All right. Well, good morning, everyone. My name is Stefan Carrera, the Education Manager here at STLE, and I'd like to welcome you to our first September kind of commercial marketing webinar today. We're here with Microtap, and they're going to talk to us about ASTM D8288, the new standard for tapping torque evaluations. And our speaker today is Dennis Mahoney, and Roger Rowley is also here. So we're going to get started. First, some of the more boring stuff, but throughout this presentation, if you have some sort of audio issues, please, you can either send a question in our chat function here in WebEx, or you can give me a call here on this that number on the screen, and I'll try to help you out as best I can over the phone. Also, this presentation is being recorded, so you will get that recording sent to you tomorrow morning. Also be aware that as a participant, you are in listen-only mode, so you can't use your microphone. But we do encourage participation. So if you can locate your Q&A panel, that should be on the right side of your screen. That's where you're going to want to send questions, and we will do questions at the end of the presentation. So again, if you have some sort of audio issues, please you can give me a call at that number on the screen, and I'll help you out as best I can. And if you have questions about the presentation or for the presenters, please put them in the Q&A panel, and those will be handled at the end. So I'm going to introduce our speaker, Dennis Mahoney. Dennis has been active in the metalworking and tribology areas for over 30 years. He is one of the earliest North American adopters of the Microtap system and has used it to develop coolants and straight oils of all types. And he's also been active in STLE, which we're very proud about, presenting multiple papers on tapping torque and other topics. We're very excited to have Dennis with us today. And also now I'm going to introduce Roger Rowley. Roger started Microtap USA in 1996. He was operating alongside his electronics business. It was formed in 1978. His training at the Lawrence Institute of Technology, worldwide work experience, and product development expertise has made Microtap USA the premier supplier of tapping torque instrumentation in North America and worldwide. So we're also very excited to have Roger here today. And both Dennis and Roger have a lot of experience to share. And I'm going to pass things over to Dennis, and he's going to get things started with us. Dennis, I'm passing you presenter now.
Thank you very much.
All right. You can share your screen, and yep, I see the first slide.
Great. So I want to thank everybody for joining STLE and us today to talk about ASTM's new tapping torque standard. Microtap USA worked closely in cooperation with ASTM and several interested companies over probably 3 or 4 years to develop the standard. Our goal today is to show how tapping torque and the LT120 tester which we make can be used to give rapid, economical lubricant comparisons. The main variables in tapping torque are fluid, tap, and test bar. For the purposes of this talk, we'll assume that test fluids are being evaluated and the taps and test bars are being held constant. We'll divide the talk into 3 sections. First off, the new ASTM standard, including a description and demonstration of the 120 torque tester. And all examples that we show throughout this talk were done on this particular instrument. Secondly, experimental work illustrating the use of the LT120 with various metals and fluids. And in the third part, we'll talk about a study of experimental accuracy and variability with 1018 alloy steel. It's very important to know if a test is accurate before you can make conclusions, or what the repeatability of a test is. So first off, a very quick review of tapping, which maybe compares it to a more common operation of drilling. In tapping, what you're doing is it's a machining process which cuts or forms threads in a previously created hole. And unlike drilling, the axial force to push down on the tap is not required because the tap pulls itself into the part being tapped by the threads as it creates them. And finally, speed or RPMs is lower than drilling, and it's dependent upon the type of thread, the material, the test lubricant, and other factors which are similar to that. Taps have a wide variety of geometries and coatings depending on what a person in a machine shop would want to do. For tapping purposes or tapping torque purposes, we'll just talk about cutting and forming taps. And a cutting tap removes metal during the process, and the chips are ejected through the flutes as the hole is tapped. This has some advantages, and that often the torque required is lower, but also some disadvantages in that if the chips eject irregularly, they may give noise or create bounces in the torque. In form tapping, no metal is removed. The metal is just deformed to form threads. This has a higher force and more lubricity is required. In general, we find that form tapping is better for differentiation of fluids than cut tapping. The shape of the end of the tap is also important. Tapping torque tests can be done with either through, that is, holes which are all the way through the test piece, or blind holes, namely that are only partially through the test piece. And this can determine the tap design. For through holes, the tap is tapered at the end, and this gives an advantage that it always seats itself and self-centers in the hole, and the tap is tapered with the first 8 to 10 threads, let's say, being smaller, so that again, it keeps centering itself through the first few rotations. In the case of a bottoming tap, it's flat at the bottom so that it can create threads all the way to the bottom of the hole. In this case, there's very little taper, and the person has to be more careful to make sure that it's centered before the operation. Just a brief description of what ASTM 8288 is. It's a lab technique to evaluate the relative performance of metal removal fluids. And it's important to realize that it's a comparative measurement of relative lubricity. And it's very repeatable on a single instrument and test series, but it's not yet verified that absolute numeric values can transfer from one type of machine to another, or from one date to another later on. So it's always best to evaluate the items you want to compare at the same time. Comparison can also be made between different fluids and fluid concentrations, operating conditions, the things you would expect. The test is applicable to all types of taps, machining speeds, and alloys that can be fabricated into a test piece. The procedure. First off, precisely machined holes are made by drilling and then reaming the test bar. Each hole is filled with test fluid, and in the case of through holes, the hole is taped on the bottom to contain the test fluid. Alternately, there are versions of the test that allow fluid to be continuously dribbled or misted onto the test bar in place of filling a hole. Torque values are measured as the tap creates the threads in the pre-drilled specimen, and typically torque values are measured every 1 to 2 milliseconds. The different variables that are commonly looked at are RPMs or tap rotation speed, the tap type or manufacturer, the size of the hole. Some holes can be either undersized to make higher torques or oversized to drop the torque, and of course the metal characteristics. Now, the ASTM D5619 predecessor procedure was very prescriptive, and a lot of testing was done in tapping torque using it as a reference, but it didn't fully follow the procedure. Here's a comparison of the old and new standards from the point of view of equipment, taps, and test bars. In the case of equipment, the 5619 device from Phalex has now been discontinued, where Microtap offers the LT120 for the newer standard, and we also have requirements in there for similar devices. This is a change again from 5619. As far as the taps go, on the older procedure, separate taps were used for each fluid, and they had to be qualified and compared before use because of manufacturing variation from one to another, even in the same lot. And then there was a complex procedure for resolving tap differences at the end when you're looking at the fluids for comparison. In the newer 8288, we use a single tap for all fluids. And our standard also includes a procedure for determining tap wear. I think it's a little more straightforward, however. Finally, the test bars. In the 5619, the test bar had only one hole, or it was a test piece more correctly, where in the newer standard, test bars have multiple holes. In the case of Microtap test bars, there could be up to 120 holes to test. This is a picture of the LT120 system, the complete system as offered by Microtap. And on the right is the tapping torque unit with a control unit on its side. And over on the left is a laptop to process the data coming from the tapping unit. Here's a close-up showing the tapping unit. The motor and the shaft is contained in the main unit with the chuck to hold the tap at the bottom. And when actuated, this shaft will descend vertically so that it can tap the test piece. And the unit also includes an XY table so that the stationary tap can tap first one hole and then the unit indexes so another hole could be tapped. So to recap, there's a single test bar for multiple tests. Each run takes about 1 to 2 seconds, and that's the reason why the data collection has to be 1 to 2 milliseconds so that you get a sufficient amount of detail. An evaluation would typically be 3 to 10 or 3 to 12 holes, and the data is transmitted to the software for rapid calculation and display. A little bit of the specifications of the unit. The tap speed is 50 to 2400. From a practical point of view, in the tests we do, we've typically had about a maximum of 1000 to 1500 RPM, but it does cover these tap speeds. The torque limit is 12 Newton meters, and this can be set manually to lower levels so that a smaller tap like an M2 will not be broken. But basically, with aluminum, the torque limits allow M2 to M12 size taps, and with steel or stainless, M2 to M10. Accuracy of torque is about 0.001 Newton meters. Then that would be on the older unit that we sold, it was Newton centimeters, but that's simply a factor of 100 different. On the vertical accuracy, it's about 1/10 of a millimeter or 4/1000ths of an inch. And then the XY accuracy as it indexes is 30 microns. There's a built-in menu system for control, which is from the control box on the right, or you can use an external PC with Toro Link software. We'll talk more about that a little later. Here's a close-up of the test bar and the tap in the chuck. The bar is approximately 12 to 14 inches long, and holes are every 4/10 to 5/10 of an inch. Here you can see 3 holes that have been pre-filled with fluid to be tested. Here are some untested holes which have been taped to prevent cross-contamination, and here are some tapped holes that have already been used for testing. If you take a look over on the right, you can see the operation of the unit where it first taps the hole and then it moves to the right, and again we'll tap the next hole. Take that back. We'll get that on the next screen. There we go. Here's a close-up showing one hole being tapped. Data is being transferred. Now the second hole will be tapped. The whole operation is very quick and quiet, and you can collect data very easily. This is the laptop supplied with the LT120, showing the software that's used for data analysis. The software is fully functional in display and analysis modes, even when it's not connected to the tapping machine. And data from the tapping machine comes to the software by Ethernet cable. So briefly on the specifications for the laptop, it can be installed because it has a site license on multiple machines. The software can control the maximum allowable torque. If you remember, I said you could lower the maximum output from the machine so as not to break a thinner tap, the RPM, and the tap travel by telling it the thickness of the test piece. It can also do data collection and analysis in all the areas shown. The software can also export data in Excel format or images in multiple formats so that it can be either archived or used in preparing reports. Now, the design of the newer unit, the LT120, is about 30 years newer, and we would expect there to be many improvements. So here are some of the changes between the older unit, which was known as the G8 or the lab tap, and the newer LT120. The design was around 1981 versus 2010, so there's the 30-year difference. The torque range on the newer unit is broader than it was on the older unit, and additionally, the RPM range is broader as well. These are important factors. The servo motor allows for smoother operation, especially at lower RPMs. Additionally, the sample interval or the sampling rate on vertical units, on vertical measurements of how far down the tap has gone, is smaller, and the data collection points or tap torque values are higher as well. The interface is another important difference. Most laptops do not come with RS-232 any longer, and therefore an Ethernet is a more viable solution. Also, the display is a little clearer and in color, and the laptop computer is Windows 10 and included in the product. One of the key benefits of the new unit is the higher torque and lower RPM limits. These work together to allow difficult to tap alloys such as Inconel stainless or titanium to be tested. The high torque tests typically require lower RPMs. In other words, as the metal becomes harder, the torque requirements are greater, and the corrective action for that is to move to lower RPMs. So in the case of testing, for example, 316 stainless at 100 to 200 RPM, this couldn't be done on our prior model, but the newer unit will do that. Also, there's a servo motor versus a stepper motor, and this has regulated speed and accurate RPMs, and the torque readings are not affected by motor noise and oscillations. It also helps in giving the lower RPM speeds. Now, typical test conditions are testing all fluids on the same test bar, and that's about 70 to 120 tests with Microtap test bars. New taps should be broken in for at least 3 to 6 holes to be certain the edge is stable. 5 or more holes would be run for each test fluid to be sure that the results are representative. And the mean torque average, or the average of the torque peak, would be in the 3 to 5 Newton meter range, because higher torques may result in premature tap wear. Also, we recommend running a control first and last, or running the first test fluid again at the end to be sure that there's no change in the tap or built-up edge. Additionally, the taps should be checked for metal fines from previous runs, and damaged taps should be discarded. The results. As we said, data is collected every 1 to 1.5 milliseconds. Each test takes only about a second, and then a few seconds to index to the next hole and allow for data transfer. And then the data is averaged and displayed after all tests are run. So let's take a look at what an actual test output result would look like. Here's the main Toro Link screen after running a test. And the torque, or the blue line, is the torque as the tap travels through the test bar. The torque is on the vertical axis, increasing as we move from left to right, which is a measure of travel through the hole. Additionally, statistical data is immediately available for this and any subsequent runs which would occur at the bottom of the screen. And finally, there's an additional graphical representation of a column graph, which is very flexible and can be set to a number of different things. Once the evaluation is done, an average curve is immediately drawn. Here's an example of a 6-run repeats and an overlapping black average curve. Again, if we look at the bottom, we see that the graph has now changed to represent all 6 of the upper curves plus the additional average curve. And any of these curves can be highlighted and changed to red, and any relative numbers will be recalculated based on the base curve which one wants to choose. Now let's move to some tapping torque examples with different fluids and alloys. And there's a number of things we might want to think about on this. One is, how do results look for different metals? How repeatable are they? And so on and so forth. And we'll get into examples of these individually. So first off, let's look at different metals. Here's an example of 3 runs from put on top of each other for different metals. The lowest one is, as you'd expect, aluminum, and then 1018 steel, and finally stainless with the highest torque values. Microtap has a number of alloys available for test. Examples are 6Al4V titanium, Inconel copper, mild tool and stainless steels, cast iron and CGI, and cast and sheet aluminum. Additionally, users can work with their own machine shops to make custom test bars. The test has been used to predict not only metal working, but also aluminum can operations. Here's an example of a titanium fluid being tapped, and here the red and the green are different fluids, but you can see that they behave almost the same, and that's due to the tap that was chosen. We'll call it tap number 1. This curve looks a little different from the prior ones because we're also measuring the torque on the way out as the tap retracts from the test piece. And in the case of steel or aluminum, typically these values are virtually 0, but in the case of titanium, there's a springiness or a memory effect, and sometimes it can be considerable. So here's a case with one tap, and you see that in the retraction area, there's no changes. But if we look at a second case with the same fluids, but a different tap, the results are quite different. And here it's clear that the green coolant is clearly better on both entry and retraction. We can summarize this data by looking at the coolants A and B and the taps 1 and 2, and the percent changes in the forward, the reverse, and the composite direction. And that's shown in this final column. It's clear that for discerning differences between fluids, tap number 2 gives better distinction. Let's move to repeatability. Here's an example using aluminum at 1,000 RPM. There are 4 tests on an aluminum test bar, and the average of the means is about 1%, or excuse me, 1.8% over the total curve. So very good repeatability. If you throw away the data on the entry portion of the tap and on the portion as the tap partially exits and completes the operation and deal only with this plateau area, then the definition, the variability becomes even smaller. In this plateau area is called the domain of definition in ToroLink. Next would be discerning or determining differences between metalworking fluids, such as choosing the best fluid for a certain operation. And the question is also, can small differences be measured? Here's an example of 4 different coolants. Clearly, there are 2 coolants that stand out and 2 in the center that are virtually the same. The 2 center coolants with intermediate torque have excellent repeatability, and they're determinable down to about 0.5% in efficiency. The extremes show low torque with good performance and higher torque with poorer performance. Here's another example of different fluids on 304 stainless steel. And in this case, we note right away that the torques are very high. The software auto ranges, and before we would have seen numbers like 3 to 3.5 to 5 here, but now we're up as high as 9 Newton meters. So between this fluid, which is the poorest performer, and this fluid, there's about a 20% difference in efficiencies. Now, let's also look at the concentration effect. Here are 2 studies, one of a fluid at 5% and then at 10%. And as you would expect, the torque at 10% is lower. But there's more to the story than that. Each of these curves is the average of about 4 or 5 individual runs. And if we take a look at the individual runs, we see that at 10%, they're very repeatable. But if we drop to 5%, there's a lot of variability. And this is pretty typical behavior. When you see variability like this, the best course of action is to move to a higher concentration. Finally, let's look at tap RPM. As we said, the instrument goes from about 100 to 2200 RPMs or 2400, but the lower ranges are really the most useful. For 1018 steel, the typical operating condition is 500 to 700 RPM. And here's an example of what those curves would look like. If we start raising the RPM to, say, 1,000, we start to see that there are aberrations and poor repeatability. And this was typical behavior with 1018 steel. 1,000 RPM would be good on 6061 aluminum, but not a good choice for steel. If we raise it to even higher RPMs, we can exceed the torque limits of the machine, and it just stops. The final topic, let's take a look at some of the experimental error and a variability in doing tapping torque. So the sources of variation, it's the tap and the test bar. And the tap is, we're worried about where over the course of the evaluation that might increase as the tap dulls out, or even decrease if the tap wears down the torque. And this would clearly be of more concern with harder metals like stainless or lower quality or older taps. Then there's the test bar to consider as well. Is there random variation because all the holes aren't the same size? Or is there some sort of systematic variation where one part of the bar performs differently from another part of the bar? So let's take a look at how we can look at this. Again, the questions are, is tap wear a factor in interpreting results? And are the holes in the portions of the bar uniform? So here's what we set up as a procedure. We used an M6 tap, 500 RPM tap speed, 1018 steel bar, and then we divided the bar into different areas with 16 holes or a 4x4 array in the center, the right, and the left, and then other areas of the bar weren't tapped. And we used a 10% commercial semi-synthetic coolant to evaluate, and we controlled the time between each test at 60 seconds. And additionally, we randomized the order of running so that different sectors, column, and rows were not systematically done. We used a random sequence generator from random.org, which is a website devoted to giving you information on that. So if we look, we can see how the test bar is set up. And here's an example. The areas that are uncolored were not tested. And there's in the left, the right, and the center, there's 4x4 arrays. And you can see that we've set up a notation scheme where L, M, and R are for left, middle, and right. A, B, C, D for the rows from top to bottom, and 1, 2, 3, 4 for the columns. So for example, this would be MC2. And if you look, you can see that there are a number of surrounding holes, obviously. But when we look at how the test was actually run, even though those holes are adjacent, they were not done anywhere near adjacent. They were done in a random fashion by comparison. So here you're looking at the run number and the hole that was tested. This is our result. It's a 48 run test, and the black line is the average of all the runs, the average torque curve. There's 38,400 data points, or 800 points per run, and they can easily be exported to Excel for further study. Here's a look at the mean value curve, and in this case, we've just looked at the plateau area from, say, 7 to 11 millimeters in the test piece. And, whoops, didn't mean to do that. The standard deviation of the means is less than 4% of the average. So it's important that your standard deviation be small in comparison to the average number that you're obtaining. So having done all this, what kind of tap wear did we get? If the tap wear occurs, we'd expect to see a progressive change in torque values. And ideally, each tap should have the same curve shape, average and max torque, but experimentally we know that there'll always be variation. So we first looked at the effect of tap wear over the series of runs from 1 to 48. And we can look at that a number of different ways. First, we can look at the run number versus the maximum torque, or we can look at the run number versus the average torque. And finally, rather than just looking at one run, we could look at 4 or 5 runs together and see how those compare to 4 or 5 runs in a different part of the test. So here's the maximum torque for all runs, and the blue line is the average of the maximum torques. And if you look as it progresses from run 1 to run 48, you can see that there's no clear drop-off or systematic variation. So we would predict then that tap wear is not affecting the maximum torque. To be a little clearer, the highest value of 6.1 Newton meters was found on run 39, the lowest value on run 7. And if you take the difference of those two, it's about 14%. Now, if we do the same kind of analysis for the mean torque, we would expect it to be more accurate because the mean torque value is derived from 800 individual points in comparison to the maximum torque, where there's only one maximum per test. This graph shows the mean value torque for the 48 against the average of all 48, which is the orange line. And again, you can see that there's no consistent variation, which is what we want. There's tap wear doesn't seem to be a problem. Looking at this, where we look at either the means of the whole curve or the means of the plateau, we see that we had the highest mean value on run 11, or the plateau mean on run 8, and then the lowest on run 34 or run 35. And these differences are about the same or a little bit less, namely 10 to 15%. The place where things really improve, however, is if you do multiple runs on each fluid. And here's looking again at it. If we look at the highest and the lowest mean torques, we see that there was about a 12% difference. But if we look at our first 5 runs as a unit and compare them to the last 5 runs, we see that the difference is much smaller. We've gone from a 12% variation for a single run to a 1% variation. So this shows both that there's very little tap wear over the 18 holes, and additionally that much better accuracy is achieved with, say, 5 runs. Now, in practice, someone might run 3 runs, and they might run 10 runs if they felt they wanted more accuracy. We didn't analyze the data with less or more. We just chose 5 as an arbitrary number. The other question is, what about the test bar? And to look at this, we looked at the different areas of the test bar. And remember that 16 holes were drilled in each section, or tapped, excuse me, in each section of the test bar. And that gives 3,840 data points per sector. And if we take the mean of all those data points, we get the same results in Newton meters for the average. So again, it's a 1018 test bar, and we're looking at the plateau regions of 7 to 11. So in this case, we have 240 measurements of the plateau area and 16 holes per section. So the mean results are the same. And within the accuracy that we're looking at and interested in, the sections of the test bar aren't a factor. Finally, our conclusions. First off, tapping torque studies with the LT120 can compare metalworking fluids. It's a rapid and an easily run test with minimal user-to-user variability because of the automation of the machine. 5-run fluid evaluation has only 1 to 2% uncertainty, and the tapping torque tests with the LT120 can successfully differentiate fluids, concentration, effects, taps, and alloys. Thank you very much, and I look forward to checking into your questions, and Roger and I will be happy to do that. Also, if you are interested in work on this with some sort of specifics for your own situation, please contact us and we can give further discussions over Zoom, for example.
All right, Dennis, thanks. We've got a few questions here. So this was in reference back during topic number 2. So someone's asking if you can comment on why there was a big difference in the taps.
I'm not certain, but let me try to get back to that point, and let's see if we can show it.
And for everyone listening, if you could please submit your questions using the Q&A section, that would be very helpful.
Okay. Okay, is this perhaps the slide that the questioner was referring to?
You're going to need to bring up, we just see your desktop right now.
Oh, sorry about that.
That's all right. You can switch your.
Yeah, there we go. Would this perhaps be the slide that the questioner was talking about?
Actually, I think it was probably the difference between the cut and the forming tap.
Okay, well, let me try to give a generalized answer that covers both. And certainly you can contact us by email if it doesn't quite address what you want. But first off, in looking at taps from a point of view of cutting versus forming, the cutting typically has lower torques. And when you do that, you're actually removing metal and ejecting it via the flutes. Now, in the forming tap, you have to deform the metal to form a thread or push it in. So it works well with something like aluminum or mild steel, which is somewhat deformable. But then if you have an extremely hard material like Inconel, for example, it's very tough to do it. So you would see a big difference as the hardness gets higher between the results with a cutting tap and a forming tap. So that's part of it. Additionally, though, if we look at the titanium graph right here, clearly these two taps are very different. And the reason for that has to do with the individual, maybe even proprietary manufacturing techniques that one company will use versus another. And they can have differences in the way the tap is fabricated, but also in different coatings that are put on them to provide lubricity. So tap company A, which is a Mugi, as you can see there, the fluids are not differentiated well. In tap case B with YMW, another tap company, and a less expensive tap, I might add, they're more easily differentiable. Want to go on to the second question, Stefan?
Yes. So someone's asking, does the ASTM procedure call for a specific cleaning procedure for the tap between different fluids?
It It does. It calls for it, but in a general fashion. It asks for the tap to be cleaned with a suitable solvent. For example, if you were doing a straight oil test with a non-emulsifiable material, it would be much better to use a organic solvent and one that evaporates, where if you're using a water dilutable, you wouldn't expect the organic to necessarily clean it as well. So let's just take a real life case where you're doing a water dilutable like we used in our study. In between fluids, you would rinse it off either with tap water and then air dry it and then pre-load it or pre-treat it with the next fluid to be tested so that you get rid of all the residue from the prior test.
All right. All right. We've got a lot of questions, so I'm just going to keep running through them.
Sounds great.
So I believe this is in reference to topic 3. They're asking is a data question. So any idea why the mean torque shown for runs 14 through 22 look very similar as the 8 runs later?
Okay, there's the 48 runs. And so could you perhaps repeat some of the question? Or
Yeah, so the question is again, the mean torque shown for runs 14 through 22, they
okay.
look quite similar to the runs they same as those for 8 runs later. Let's see. So he's saying the bar chart.
Perhaps this one here.
Yeah, let's see.
Or more to the point, this one here.
Yeah, I believe that's so I guess the question is then with that chart, then you have 14 through 22 are about the same range. So I guess he's asking why 14 through 22 looks like 34 through 42. He's saying.
I'd have to look into that more carefully. I can see that there are small differences in the variations from one to the next, but I can't off the top of my head say why those particular areas should look the same. And I can, after this talk, we can look into what parts of the bar were being tested in those areas and see if that sheds any light on it. But remember, each of these runs, as you progress from 1 to 48, is from a different area of the bar. So it's hard to conclude something about the bar or the area of the bar from the run.
Right. So that question from a Steve Schaefer, if you want to email Dennis or Roger, then they'll be able to get back with you with a more detailed answer later. All right, I'm going to jump to the next question because we've got a lot. Does the software evaluate the data according to ASTM 8288?
Yes, I would say that it does. The reason I say that is that 8288 was written around this device and the software that it uses. That sounds a little bit like a circular answer, however, but to go on, the 8288 and the software both measure torques and efficiencies in comparative fashion. So in that case, I think this software does conform to 8288, but I would expect other calculations to conform by other devices to conform as well.
Okay. All right. Another question. What about repeatability testing on the 6061 aluminum? Is there a correlation to repeatability and pH?
We have never done a pH versus repeatability study. And I think by that, maybe you mean choose a pH and run multiple tests, and then choose a different pH and run multiple tests. In general, I will say that over the range of typical metalworking fluid pHs, namely 8 to 10, we see very good repeatability with aluminum. Now, if you were to vary the pH from a low value like 8.2 to a higher value like 9.7, then I would expect to see changes. But I would expect under either circumstance that there'd be good repeatability.
Okay. Someone's asking, is the European material the same as the US material?
What do they mean by that precisely? I'm not sure.
Well, let's see if we can get them to clarify. While we're waiting for clarification, let's go to a next question. Have you done similar reproducibility studies on harder metals such as 304 or 316 stainless steel?
No, we have not. In general, I would expect the repeatability to be somewhat less, but I would still expect to get good differentiation by using multiple runs. And the reason I say that, I think, is because as you go to harder metals, then you may get a spike or noise or stick slip as the tap progresses through the workpiece. We have done a lot of studies to evaluate fluids on harder metals, and we get good results, but we haven't done a 50-point test like this.
Okay. So is it obvious to know when the tap is worn out?
I think the best way to run tapping torque and to determine that, because it's obviously a worry, is to use a constant fluid. And when you're running the tapping torque unit on different days or now and a week later, to run a brief test with the fluid of interest or the reference fluid, let's call it, to see that the values are the same. For example, if you had a lot of tap wear, you may see the values of the torque increase for the same fluid. A more serious concern is that you might be testing, say, 5 fluids, and let's pick a fluid. Fluid number 3 is a very poor lubricant, and it gives tap wear under the values or the ranges you're using. So there, if you see a sudden jump, you might retest fluid numbers 4 and 5 to see if they were, or let's say fluids number 1 and 2 before number 3, which was the poor one, and see if they repeat. If they don't, then I think the best thing to do is to use a new tap and to maybe run number 3 last, or to make the conditions less severe by lowering the RPMs or raising the concentration.
Okay. So another question, did you weigh the taps to determine wear, or did you use a qualitative assessment like a microscope or something like that?
It would be qualitative. And the main way and we didn't weigh them. I don't believe that our balance would be sufficiently precise to determine differences in weights. The main thing that we were looking for was a variation in torque, because we want the test to be measuring the variation in fluids and not the variation in taps.
Okay. So we have another question. How does chatter affect the overall torque value?
I don't think that chatter affects the overall torque as much as it affects the readings that you'll see on the individual runs. And maybe we can get to that. If we look at, I believe we had a test of 304, which is a tough to tap material. Let's take a look at this run here. Not seeing what I want to see. Well, I apologize. It's not coming up where I want it to on the screen. But at any rate, the 304, if you can remember, had a lot of spikes, high frequency spikes or noise. And that, I believe, is due to the chatter, which is what we're talking about.
Okay. So going back to the earlier question about your European material, you're saying it's not the same material that is on sale by the German company Microtap .de. The reference is not the same as the US one, but they want to know if they can consider the observations to be the same between.
I believe that the observations will be the same. We haven't done, as I said, we did all of this work with the machine that we now sell, the LT120. The two companies, Microtap Germany and Microtap USA, are different companies, and the hardware and the alloys that are used in the tests are somewhat different. But in answer to the question on test pieces, for example, and this would include even the alloys that Phalanx used, I believe that the results would all be representative of the other company's work.
All right.
If I could get in, Dennis, on the reference for the Europeans are on a DIN standard, and we're using the ANSI standard. And on our sheet, we have a comparison of there's equivalencies, but not specifically, just by the use of a different DIN and ANSI standard.
Right.
All right, thank you. All right, let's see. There's a lot of questions, and I'm not sure if we have time to get to them all, but let's grab at least a few more. So here someone's asking, is there any relevance of the test results to other metal cutting applications, such as sawing, honing, or milling?
Yes, we believe that the correlation is good, even to the extent of, I mentioned aluminum can D&I. We've had good predictability with our results. And the reason for that is at least partially, I think, due to the fact that a tapping operation with forming requires fairly high pressure and is a good measure of lubrication. We've never tried to relate it to grinding, so I can't really comment on that. Mm-hmm. But in general, I think the correlation with the more typical operations like milling or drilling is good.
Okay. And someone's asking, is there a recommendation table of RPM versus bar material for test reference?
Yes, on the Microtap website, there is a reference, and it's enclosed with it is the offerings of the different alloys and materials that Microtap USA has, and then there's also RPM references or recommendations there.
All right, great. And let's do one final question before we wrap things up. Does the ASTM standard already have a reproducibility statement? So multiple labs and machines.
No, we're in the process of doing that. We do have the reproducibility on our own machine, but our next step is to go out and work with other labs where we test under the same test conditions and with the same materials so that we can develop a lab to lab and a machine to machine standard. I will say that Microtap has sold a number of LT120s, and in one case we measured the standard machine that we have and took the same test pieces, tap and fluid, and tested them out on a new machine that was being ready for delivery. And we got, I believe, a 1% to 2% variation between the two.
Okay, great. Well, Dennis and Roger, why don't you put your emails back on the screen so people can get another chance to jot those down. We're running out of time, so we apologize if we couldn't get to your question, but you can always, you can please reach out to Dennis or Roger, and they will be able to answer your questions kind of further. I will also be, tomorrow I will be sending out the link to watch the recording, and I will also be sending out the emails where you can contact Roger and Dennis as well. Roger, Dennis, do you have anything you'd like to share before we sign things off?
No, I just want to thank everybody, and Roger, I'll let you give your thoughts on the subject too.
Oh, I think it was hopefully beneficial to everybody, and we've got a lot of work into it, and anxious to deal with you individually as you come, with email or whatever.
All right. Well, everyone, thank you for joining us today. And I guess Dennis and Roger's information is on the screen there. And if you have further questions or comments, please reach out to them.